welcome back. So for those, I mean, of course, all of you still remember what we did last time, but I still repeat that, at least for my own purposes. Do you understand me in the back? Is this fine? Yeah, okay, thank you. So we had considered a little bit the model, right, which was the James-Cummings model, and I didn't get to finish that last session, and actually today I will finish it, and then I will, go towards the Floquet theorem, which is a little bit, in some sense, a generalization, if you wish so. And probably the Floquet theorem will also occupy me in the next lecture next week, right? We'll see. But the idea was essentially that we wanted a minimal model where we have 2 degrees of freedom, 2 fully quantized degrees of freedom. On the one hand, a 2-level atom, which is a qubit, let's say an atom, qubit, spin 1/2 system. You take your favorite experimental or physical incarnation of that, right? And so I'm, by training, an atomic physicist, and also the type of experiments which are done typically are often done in this context. So we imagine this 2-level atom which has a ground state and an excited state, right? Which has an energy splitting which we call omega. So at some point, let's say now this is of course a frequency, so at some point I will treat frequencies and energies on the same footing by essentially setting h bar equal to 1 or measuring everything in units of h bar, what this means, right? So that's my 2-level atom. Right, and remember, if you can't, if my handwriting is difficult to decipher, you just ask, please, okay? So don't be shy. And then the idea was that this is now coupled, and in an experiment, you have it all often coupled to, for example, a single quantized mode of the electromagnetic field. How do you do that, or how do you isolate such a mode? By putting mirrors, by defining the proper boundary conditions. So a typical picture which you might see is something like this. So this is one mirror, right? This is another mirror. And then the idea is that you have something like by classical optics, you have some confinement, the waist of your field mode, right, which has then standing wave structure, right, and corresponds is nothing else in the quantum mechanical description then, but a 1-dimensional harmonic oscillator, right? So that's a 1D harmonic oscillator with eigenfrequency which we call capital omega. Right, and then we still need a coupling between these 2 degrees of freedom, which we call V. And so this is a single mode, single quantized mode of the electromagnetic field, which then in field quantization, right, which builds up on your classical description of an electromagnetic field, of the free electromagnetic field, of which you know that the energy in a certain volume is given by the square of the electric field and the magnetic field component. So it's a quadratic form, and this then at the end allows you to write this as a harmonic oscillator, what I didn't show you in detail, right, for reasons of time. And so the idea is now that we want to efficiently, I'm not sure whether the micro works. Is it working? Yeah, it's working. Okay, good thing. Thanks. So we want a way to efficiently transfer excitations from 1 degree of freedom to the other, right? And so we decided by this example of a swing, which we already know of classical mechanics or from the driven classical harmonic oscillator, that this would best happen at resonance, right? So we assume a situation where the eigenfrequency of the system which is driven, which is the atom, is close to the driving frequency capital omega, right? So and we wrote the interaction as follows. Inspired still by the classical description. So the interaction V is now still with units like the charge of the electron, which is bound to the nucleus, right? So then now look. There was a question. I'm sorry for this. This is meant to be an F, a capital F. Okay. So some of you after last lecture asked me whether this is a plus and a minus. No, a plus minus might look similar, but this is meant to be an F. Okay, so this is an F like this maybe. Anyway, so it's meant to be the amplitude of the driving electric field, right? And then you assume that we assume without much loss of generality that field be linearly polarized along the x direction, and then you take cosine omega t as this periodic driving, right? And so then if we take the field vector f parallel to x, right, and the k vector, so the wave vector along the z direction. And then we take near resonant driving, near resonant driving, which means that we assume that omega is roughly equal to capital omega. And then from that we inferred the total Hamiltonian, so the total energy of the system composed by the atom and the field and the interaction between both. So, and I didn't give you this terminology yet, so that's also known as the dressed state Hamiltonian. The dressed state, I write it down first, dressed state Hamiltonian. Yeah. So this is the state of the atom dressed by the electromagnetic field. Okay. So dressed state of the atom which is dressed by the electromagnetic field. Yeah, so that's the jargon, or that's the thought behind the jargon. And just a little bit of theory, of history. Sorry. So this was essentially done by Serge Roche and Claude Contanucci. In the 60s, roughly. This was actually the habilitation thesis or thèse d'état of Serge Roche, and this is also known as in the French original, right? I heard that we have French people in the audience, right? So this is Atomavillé. Okay. Okay. And so this total Hamiltonian now looks as follows. So H equals the Hamiltonian of the free atom, right, which is just our two-level system. So that's essentially sigma z, right? Done. Then plus the Hamiltonian of the free quantized field mode, which is a harmonic oscillator in creation and annihilation operators, right? And then plus the fully quantum translation, essentially from this classical interaction Hamiltonian, which I wrote down there, given by A plus A dagger times sigma plus sigma dagger, right? Where these are the annihilation and creation operators of the harmonic oscillator, of the one-dimensional harmonic oscillator of frequency capital omega, and this is the lowering and raising operator of the two-level atom, right? And so this we also would write H atom plus H HO plus V. Yeah, and here it's important that you remember, or that you hardwire this terminology dressed states, right? So it's the energy of the total system of the coupled system of atom and field together. And now we want to solve we want to get an idea of the solution of the Schrödinger equation, which is generated by this Hamiltonian, right? So we want to get an idea of the time evolution of a state of atom and field, of the time evolution of such a state for a given initial condition, right? And we assume that we know the dynamics of the bare atom well, so we have it diagonalized. So since we have diagonalized, we know its unitary evolution operator, so we know everything about any state of the atom as it evolves in the future. Likewise for the quantized harmonic oscillator, but we do not yet know how the total system composed of these 2 degrees of freedom would generally evolve in time, right? And so therefore, given that we assume that the dynamics generated by the atomic Hamiltonian and by the harmonic oscillator Hamiltonian is already known, so that's in some sense the trivial part because we already know it, we split the time evolution induced by the interaction part of the Hamiltonian from the time evolution generated by the unperturbed part of the harmonic oscillator and of the atom, right? And for this we use what is known as the interaction picture. So now comes something new, which I just discussed with some of you after last lecture very briefly. But then I learned that you maybe have not seen that yet, so therefore I give you a short description how this is done. So now we go to the interaction picture. Yeah. For the to infer time evolution induced by age. So in general, you solve the Schrödinger equation in a Schrödinger picture, or that's what is often done, right? So there, all the time dependence is typically, at least for time-independent Hamiltonians, is typically carried by the states of the system, right? And then you have heard about the Heisenberg picture, where essentially the time dependence is mapped over to the operators, right? And hence to the eigenstates, and hence to the coordinate system, if you wish so. And now the interaction picture is something intermediate between the Heisenberg and the Schrödinger picture. So intermediate between Heisenberg and Schrödinger picture. Yeah, and you do essentially the following. Now assume you have the Schrödinger equation. Oops, something happened?
Shouldn't that should be induced by V as of the age?
Okay. So I didn't specify anything. Yeah. So V as a special ingredient of that. Okay. So, but the time evolution is still induced by age. I just, let's say that there's a trivial part which will be induced by those, right? And there's a non-trivial part induced by those. And I will now extract this non-trivial part in the next step. Okay. So the Schrödinger equation, as you know it, right, is I h bar dt psi s. Now this s explicitly says that I mean the state in the Schrödinger picture equals h naught plus v psi s, right? And now I do the following definition. So I define the state, the system state in the interaction picture, thus the index I here, right? I define it by multiplying from the left, this one here. So, yes. Yeah, so I multiply from the left e to the plus I h naught t over h bar, given that the total Hamiltonian is written as h naught plus v, right? So now you know that if v were vanishing, right, so then the time evolution of psi would be given by e to the minus I h naught t over h bar. So therefore, applying from the left e to the plus I h naught times t over h bar just compensates this free evolution part, okay, which is generated by h naught, right? So, so like this. Didn't finish the definition, right? And so therefore now I can rewrite this in terms of psi I. So therefore I get I h bar dt, and then I have psi s is now e to the minus I h naught t times psi I, right? So e to the minus I h naught t over h bar psi I equals h naught plus v times e to the minus I h naught t over h bar psi I. Yeah. So now I do this here, so then I get I h bar, and here I get an I h naught over h bar, so I essentially get something in h naught times e to the minus I h naught t over h bar psi I, right? Plus then this prefactor times the time derivative of psi I, and on the right hand side, okay, I just multiply that out, so I get, how do I do this? No. Okay. So I essentially get h naught times e to the minus I h naught t over h bar psi I plus e to the minus I h bar H naught T over H bar I H bar dt, yes, psi I equals H naught e to the minus I H naught T over H bar psi I plus V e to the minus I H naught T over H bar psi I. Right, and so this and this goes away, right? And so I'm just left with this part and this part. So I get e to the minus I H naught T over H bar I H bar dt psi I equals V e to the minus I H naught T over H bar psi I. And so now if I multiply now from the left with e to the plus I H naught T over H bar, right, I get I H bar dt psi I equals V, and this I call Vi, times psi I, where Vi equals e to the I H naught T over H bar V e to the minus I H naught T over H bar. Right, and so this is now the Schrödinger equation in the interaction picture, right? And so the important part of that is that what you have to recall is that in the interaction picture, the dynamics of the state is generated only by the interaction part of the Hamiltonian, right? Okay, and so this now you essentially use, in this case now, and you identify now this part here with H naught, right? And then you apply essentially this transformation. Right, and then you get, after some, I mean, there you have then to do a little bit of operator algebra. So, but anyway, at the end, then you find, so now, yeah, for the interaction Hamiltonian, or yeah, interaction term, sorry, interaction operator in interaction picture. Yeah, so then you find Vi, and for reasons of time I don't show you now the detailed calculation. If you don't if you don't succeed to show what I now give you as a final result, you send me an email or you see me in the office, right? Then we can look at it in detail. So then this essentially you start with that. So EI atom T over H bar EI H harmonic oscillator T over H bar times V times e to the minus IH atom T over H bar e to the minus IH harmonic oscillator T over H bar. And this then, after some calculation, gives you H bar G. And now that's going to be a longer expression, okay? So H bar, something you cannot read? Everything okay? Okay, good. So now A sigma, right? And times exponential of minus I capital omega plus omega times T plus A sigma dagger, right? And you see now, I mean, at least you can guess, right, that, I mean, here you know that the atomic Hamiltonian is something in sigma and sigma can be written in terms of sigma and sigma dagger, right? And the harmonic oscillator can be written in terms of A and A dagger. So that's why it's not a surprise really that you get expressions in A and sigma. And so then, I mean, let's say it's altogether 4 terms. So then you get e exponential minus I times capital omega minus omega times t plus a dagger sigma exponential I times capital omega minus omega times t, and then plus a dagger sigma dagger times exponential, and then here you have I times omega plus omega times t, and here the curly bracket closed. Okay, so that's now already an important, or a very important intermediate result, right? So now what's the interpretation of these different terms, right? So on the one hand, you have this action A and sigma. So if you have A and sigma, what does it do with your harmonic oscillator and the atom? So what does sigma do? Okay, I mean, sigma, does it add an excitation to the atomic degree of freedom, or does it take out an excitation from your atomic degree of freedom? So we take a vote. Who is in favor of, I mean, and abstentions are not allowed, okay? So otherwise we will have to do a recall, right? Who is in favor of sigma taking excitation out of the atom? Who is in favor of sigma adding an excitation to the atom? Who is abstaining? Okay, good. Okay, so it's taking out an excitation, right? And so sigma is taking out an excitation, and A is doing what with the harmonic oscillator? Look, I will not continue until there's a signal from the audience. You want to have lunch. I'm used not to have lunch. Okay, so please. What does A do with the harmonic oscillator? It takes an excitation out, right? Yeah. So therefore, what does this term here do with the total energy of the system? What is this term A sigma? What does it do with the total energy of the system? A sigma, right? Now this is an operator. It will act upon states of the harmonic oscillator and of the atom, right? So we are living, I mean, let's say the total system is living on a tensor space, which is built by the Hilbert space of the atom, which is a 2-level system, right? And the Hilbert space of the harmonic oscillator, right? So therefore, the states will be tensor products of, I mean, a certain number state of the field, right? And the ground state or the excited state of the atom. So now, what will the application of A sigma do with the energy of the system? Will it leave the system energy invariant, or will it change the energy of the system? So who thinks it will leave the energy of the system invariant? You see what I mean? Okay. Do you see what I mean? Okay. So I have. So now assume I'm here. This is my initial state, right? So then this would be n equals 0, n equal 1, n equal 2, and this would be the excited state. So the total energy of the system is then how much? Essentially something like 2 omega, right? 2 omega plus omega, if you forget about the ground state energy, right? So now what will happen if you apply these two operators? Then what will be the energy afterwards? Capital omega, right? So the energy is not conserved, right? So while what does happen with this term? Is here the energy conserved? Or let's say, which of these 4 terms conserve the energy of the system? Which of the 4 terms leave the system energy invariant? Where? Ah, bravo. Okay. A sigma plus and A dagger sigma. Prima. Yeah. So, okay. So, therefore, we have... Yeah, so we have energy conserving terms. Which are these ones, right? They are energy conserving. Yeah. And these ones are energy non-conserving. Yeah. So now what, I mean, and then do you see a typical time dependence which is associated with the terms being energy conserving or energy non-conserving? And remember, which was our assumption for this interaction? How did we choose the two frequencies? How did we choose the two frequencies to have an efficient transfer of excitations between the degrees of freedom? Resonantly, bravi, okay? So this means this, right? So what does this mean now? If you stare a bit, if you compare now the time dependence of the energy conserving terms and the time dependence of the energy non-conserving terms, do you also see that this property of being energy conserving or energy non-conserving is correlated with a certain typical time dependence given this condition? So in which respect, in which sense is this time dependence very different from this time dependence if I'm close to resonance, if I claim or if I require this resonance condition? So are there terms which are oscillating faster than other terms? I'm asking a question, yeah? Are there terms which are oscillating faster than other terms? Are there terms which are oscillating faster than other terms? So look at this, right? So you have an interaction Hamiltonian, right? And you have, I mean, energy conserving and non-conserving terms, and you have time dependencies which have a certain characteristic frequency. And my claim is now that they separate in some sense. Their typical time dependence is happening on different time scales under this condition. Right? And you see that if omega is capital omega is close to small omega, right? Then you see that this term essentially does not evolve in time. It's essentially stationary, right? So you can make it arbitrarily close to zero. You can make the frequency arbitrarily slow, right? While this here, I mean, if you compare it to zero, is arbitrarily large because it's 2 times omega. Okay? So that's why you call these the rapidly oscillating terms, and that's the slowly oscillating terms. And so what you see is that, and this now is conceptually quite important, so you should remember that, is that, I mean, associated with this resonance condition, the resonance condition allows you to observe a separation of timescales. Separation of timescales, right, which are associated with the let's say, energy conserving versus the energy non-conserving. Terms, okay? So the energy conserving terms essentially are almost stationary in time, while the non-conserving terms are oscillating rapidly, right? And therefore, you can argue, if now you integrate the time evolution equation, which is generated by this Hamiltonian, by this effective Hamiltonian interaction picture, that you can, the rapidly oscillating terms average out, right? While the essentially time-independent part of the interaction Hamiltonian are dominant and will survive this averaging procedure, right? And so there's, I mean, let's say there's different ways of this argument. So you find in literature, you find, I mean, different phrasings, if you wish so. One is by energy conserving versus energy non-conserving. And we will see it again, let's say, hopefully next week, right, if I get there. If we look at a special case of the Floquet theorem, I mean, then we will understand that this is some sort of perturbation theory to throw away the rapidly oscillating terms, right? But it's also throwing them away. We will call it here the rotating wave approximation, right? But in a different context, in the context of this theory of open quantum systems, that's what we also call the secular approximation, which is actually a terminology which comes from classical dynamics, or perturbation and classical perturbation theory, right? So therefore, so the separation of timescales, right, it makes your life easier, right? Because you will be able to say, at least on average, you can throw certain terms away, right? And so therefore, it's a widespread, it's something which is widespread in theoretical physics. It comes under different names, so we will call it, I will write it on the next page, rotating wave approximation, but it also comes under the name secular approximation. Also, in some sense, it's also an adiabatic approximation. Right? And secular approximation is origin, as I said, comes originally from classical perturbation theory. And adiabatic, why adiabatic? So I mean, which is the association which you have in mind when you hear adiabatic? Who already heard the term adiabatic? I mean, show me your hands. I mean, I need a signal, right? So make an effort. Who already heard the term adiabatic? Who never heard the term adiabatic? I mean, it's not a problem if you didn't hear, but I'd say many people didn't give a sign, so you didn't. Okay, bravi. Okay, look. So adiabatic is a term which you typically use in equilibrium classical statistics, right? So for example, you cool down a gas in an adiabatic way or so. So it essentially means that you give it time, right? So it's essentially a slow process, and so also in quantum physics, you talk about adiabatic processes, which again are essentially processes which occur in long time scales, or which are associated with slow time evolution, right? And in this sense, I mean, let's say you might also call this an adiabatic approximation, which we are doing there, right? So, but I'm just saying the point is that it's terminology from different fields, right? And so you have to take it with a little grain of salt, because people typically tend also to associate slightly different pictures with these terms. But at the end, I mean, what I'm trying to say here is that this is very closely related. Here you find this also in the theory of open quantum systems, right? This here you find in all kinds of quantum control scenarios, right? And the easiest version of that is now what we will now do on the next page, which we call the rotating wave approximation, okay? And but then what you have to see also, let's say, is this separation of time scale, right? It goes away. You cannot do it anymore as soon as you deviate too strongly from the resonance condition, because it's only under the resonance condition that this frequency is very different from this frequency, okay? Only under this condition. Okay, so now, given omega roughly equal to omega, right? Yeah. discard the rapidly oscillating terms which are proportional to exponential of plus minus I capital omega plus small omega times t, to keep only the energy conserving terms. Right? So in some sense, as these terms are energy conserving, you can also conceive that as the coupling of energetically degenerate states, right? So in some sense, it's a little bit reminiscent also of degenerate perturbation theory, but it doesn't come out here very explicitly. We might see that again in the Floquet picture then later. So given the resonance condition, right, we discard rapidly oscillating terms, right? And so to keep only the energy conserving terms with slow time dependence exponential plus minus I times omega minus omega t, right? Hence, take advantage from separation of timescales at resonance. Yeah, so this means that if you drive a system at resonance, you will find certain terms which are dominant because they evolve slowly in time, right? And so, so this and this procedure, this neglect of the rapidly oscillating terms, that's what is in this context, bless you, called the rotating wave approximation. Yeah, so in the jargon also RWA. Yeah, you find that from time to time when you find technical papers, you look, and then people just say, I mean, let's say, assuming R, or we do a RWA, right? So that's what they mean, right? And then with that, you get the new form, and this is now what is called, or what is known as the Jaynes-Cummings interaction operator, right? That's what we were after, which is now H bar G. So essentially, you take that, right? You skip the terms which are non-energy conserving and rapidly oscillating, and then you are left only with A sigma dagger exponential of minus I omega minus omega times t plus A dagger sigma exponential I omega minus omega times t. Yeah, and so this is the Jaynes-Cummings interaction Hamiltonian. Let's write it down. Jaynes-Cummings interaction Hamiltonian. At resonance, so we assume that omega minus omega is close to 0, right? And so now we give this a name, which is also called the detuning. It's again a little bit a jargon or a technical term. So what we say at finite detuning delta equals omega minus omega. Right, and the sign here doesn't matter. So I just now, without a loss of generality, define it like this. You can also define it in the other way. Doesn't matter. So important is this terminology, finite detuning. Right, detuning is delta. Not being equal to 0 is finite. Right, and this is the Jaynes-Cummings interaction Hamiltonian. Right. And so often you hear in the jargon, when you hear talks about, I mean, quantum information, when people talk about reaching strong coupling in their specific experimental setting, they say we drive the system at finite detuning, and then this is essentially the mismatch, right, between the free frequency of the driving field and the free frequency of the unperturbed target, material target. Okay, so now we already observed, right, with this energy conservation that, and so this is now one observation. Yeah, so VI or VJC mediates transitions only between states n plus 1 and G, right? So n plus 1 excitations in your harmonic oscillator and the atom in the ground state. And so this is coupled now by this Hamiltonian to which state? So which state is this coupled to? I mean, this state, if you apply this Hamiltonian to this state, what do you get? N and G plus 1. And G plus 1 is what? E. E, okay. Yeah, so this is, I mean, just for the notation, right? And so mediates transitions only between this and NE, right? Okay, and so that's essentially the counterpart, or that's the consequence, right, of having dropped the counter-rotating terms or the rapidly oscillating terms. Okay, so that's now another jargon word which I just used, counter-rotating, right? So the terms which are slow, they are called the co-rotating, and the counter-rotating are the rapidly oscillating terms. And again, this rotation will become clear then when we are at the Floquet picture, or this term, I mean, it's terminology of counter-rotating and co-rotating, right? So you're always only coupling these manifolds. Now what we are interested in, so now we want to infer the dynamics of arbitrary state of the atom and the field, right? Psi of t in the interaction picture given as C n E of t and n and E plus C n plus 1 and G of t t times n plus 1 G, right? So now we want to infer the time evolution of such a state where we, for example, then define certain initial conditions of these expansion coefficients in the unperturbed basis. And so to do that, now we plug this into our Schrödinger equation in the interaction picture, which has gone. Okay. Anyway, so let's take this one. Right, and so this ansatz in the, so psi of t I into Schrödinger equation equation in interaction picture gives, right? So on the, of course, I get IH bar time derivative of this, right? Is IH bar time derivative of this. These states are time independent, so I get time derivatives of these expansion coefficients. So I'm essentially working in the amplitude formalism, if you wish so, right? And then I take the right-hand side of the Schrödinger equation, which is just generated just by the application of V upon this state, right? So then I get, and I abbreviate it a bit, right? So you get, well, should I? Yes, I think I can. So, right, so you get psi dot, right? And then you want to extract the time dependence of CNE and the time dependence of Cn plus 1g individually, right? You will have on the right-hand side, you will have an expression in NE and N plus 1g, right? So therefore, from the left-hand side, you filter it out by projecting from the left either NE or N plus 1g upon this right-hand side of the equation. And by this, then you extract the time dependencies of these two expansion coefficients, right? And doing so, you get that CNE dot, right, which is the time derivative, equals minus I times g times square root of n plus 1 times e to the minus I. Now, I use this short form of the difference between the two frequencies, omega, capital omega and small omega, right? The detuning t times Cn plus 1 g. And I get, likewise, I get Cn plus 1 g, so the expansion coefficient of the other basis state of the atom plus field Hilbert space, right? I get minus I g times square root of n plus 1 times e to the plus I delta t times Cne. Right, and now, I mean, let's say you have these evolution equations in the Jaynes-Cummings picture, right? And now we solve this. I mean, we just want to see at least a qualitative picture of what this dynamics does now, and we solve it for the special case at resonance. So solution at resonance. So now at exact resonance, meaning that we set the detuning precisely equal to 0, so both frequencies precisely match, right? And for the initial condition, Cne at time t equals 0 equals 1, and Cn plus 1 g at time t equals 0 equals 0. Okay, so the atom is initially in an excited state, right? And the harmonic oscillator is in the state n. So let's say, so this is the excited state, and tensor, right? N. Okay, so that's my initial state. And if you do that, so then you find bless you. So then you find, now you can be interested in different things, right? So you could be interested in what's the excitation of the atom as a function of time. So what's the probability to find the atom, for example, in its excited state as time goes on, right? Or you can ask, what's the number of photons which you find in the cavity mode or in the oscillator mode, in the quantized field mode, right? And so you look at different observables given these initial conditions and given that you are precisely at resonance. And so, for example, you look at the excited state population, which is excited state population. Yeah, which is given by psi of t, and yet now you project out the excited state, right? And take the square of that. And this is also then written often as psi sub p time sub e as a function of t. And there we find that this is cosine squared of g times square root of n plus 1 times t. Bless you. Okay, so this you essentially do by solving these equations with these initial conditions, right? Then you project out, you project it onto the excited state, and then you get this expression. So you see that you start out at 1, right? And then you do a periodic, as people then say, Rabi oscillation with a certain frequency, right? And another quantity which is interesting is now the number of photons in the field mode. So this would be now psi of t a dagger a, which is the photon number operator. So it counts the number of photons, the intensity, if you wish, so of your field mode, right? And psi of t, right? And this then gives you n plus sine squared times g square root of n plus 1 times t. Yeah, so it oscillates between n and n plus 1, right? And then another quantity which is still of interest is the variance of your photon number, right? Which you find then to be, I have to stop at 10 past, right? Or 5 past? Okay, right. Then you get 1/4 times sine squared of 2g times square root of n plus 1 times t. Okay, and now comes, to close this chapter, comes a picture, or come a few pictures, right? So now, how do we do that? Yes, should fit. So let's do it like this. So it will be a large plot, okay, so you need space. So this is time. And here now come different, panels essentially. You see, 1, 2, zack, zack, zack. Okay. So here I plot the excited state population. Let's say here is 1, right? Then so this is essentially multiples of pi over 2 or something like this, right? So now we have first this oscillation here of the excited state population. We start in 1, right? Then we get, how do I do it? Like, let's do it like this. Essentially like this, right? So that's the excited state. Then correspondingly, since the total energy is conserved, right? So the ground state population would then go like this. Oops, no, sorry, already wrong. So like this, right? So this is PE. This is P ground state, right? Which is has just the other time dependence. Then the number of photons. So you see now here, essentially the atom releases its excitation, gives it into the cavity. So now the excitation has to be in the cavity, right? So therefore, the time evolution of the photon excitation essentially goes like this, or the photonic, right? So where this here is the level n, right? And here is the level then n plus 1. And the variance, just has, where are we? We are there, right? So it has just twice the frequency. So it's also clear, let's say the uncertainty about the photon number, right, is largest here when you're essentially halfway between n and n plus 1, right? So therefore the variance has to peak here. oops. Yes, I mean, the idea is that it goes. See that? Okay, so that's the variance. So and so you see that essentially the excitation is exchanged between the 2 degrees of freedom, right? Between the atomic degree of freedom and the field degree of freedom. So that's what you also call then playing ping pong between the 2 degrees of freedom, right? And what is important here is that now this also happens, right? This also would happen if n equals 0, right? So first, and it's also for n equals 0. So if initially, right, you have no photon in the cavity, right? Still, you would see these Rabi oscillations. So also for n equals 0, and then this you call this vacuum Rabi oscillations. Yeah, and so these dynamics in general, these oscillations are called Rabi oscillations, right? And the Rabi frequency, is 2 times g times square root of n plus 1. Okay, so that's important terminology, right? And okay, so maybe ex post it's actually not so surprising, but this vacuum Rabi oscillation, right? It was in some sense it was a big deal when this was also observed first time in experiment. Okay, so this would conclude the yes. So this would conclude the chapter on the Jaynes-Cummings interaction, right? So Jaynes-Cummings, as I said, it's the resonant coupling between, so what were the important ingredients, right? So resonant coupling between 2 arguably simplest degrees of freedom which we can imagine, right? On the one hand, one-dimensional quantized harmonic oscillator. On the other hand, the 2-level system. Resonant driving. Resonant driving allows what? In which kind of simplification? What did the resonant driving allow us? What did it phenomenologically induce in a time evolution? The separation of timescales, right? The separation of timescales allows us to make which approximation? Louder, please. Adiabatic, or what was the technical term now here, specifically here? Rotating wave approximation. Great, right? And then what we get phenomenologically is this Rabi type of dynamics, these Rabi oscillations, right? With the characteristic frequency, which is given by the coupling constant. Coupling constant, this I showed last time, right? This essentially encodes the coupling strength between the field and the atom. So it's, in particular, what goes in here is the atomic transition matrix element, right? And n plus 1, square root of n plus 1, do you have a physical interpretation for the square root of n plus 1? Where does the n plus 1, where does this prefactor come from? This square root of n plus 1. So you know it. You have seen it already in the action of the annihilation and creation operators upon the eigenstates of the field, right? So what does A do with the Fock state n? Or let's say this. Okay, so this gives me what? So this is an energy eigen. Speak up, please. Loud. Yeah, so it apparently comes from the application here, right? So now what is A dagger A on n? All? N? What comes? You have to tell me what I have to write, otherwise I cannot write. Yeah? So now if you assume that n is very large before with respect to 1, so you see that this is essentially, I mean, this is the square of that. So now the number of photons, if you have a light field, the number of photons, what does it tell you about the light field? The number of photons. If you have a light field, you have a certain number of photons. What does it tell you about what physical property of the light field does the number of photons which are in the mode tell you? I mean, when it's many photons, is it bright or is it dark? Is it faint? It's bright, right? So it's a bright light. There's many photons, so the intensity is high. So actually, the number of photons is essentially the intensity of the light field, right? So therefore, the square root of the intensity gives you what? The square root of the intensity of a classical light field gives you what? No. Power? No. Let's say when you have the intensity, so the intensity of a light field is given as the square of what? Of the amplitude. Who was this? Ah, bravo. Okay. Yeah. So therefore, in turn, right? This essentially means that this is something like the field strength or the field amplitude, right? So this means the Rabi frequency is given by essentially coupling strength and the strength of the light field. Okay. Okay, good. So now, since of course, again, I didn't get where I wanted to get, so maybe just a perspective on what we do then next time. Right, I give you a question, okay? So now we were considering essentially a Hamiltonian, which was H naught, right? And I lumped together in H naught. Now I lumped together the atomic and the harmonic oscillator part, right? Plus something like, let's call it now lambda times cosine omega t, right? Something which was this driving term, right? And from this then we derived this form sigma plus sigma dagger times A plus A dagger, right? So now, yes. So now my claim is that, I mean, first ask yourself, is this a time dependent? Is this time dependent? Does this define a time dependent problem? Or actually a time independent problem? Independent, yeah. Yeah, so because of course it is time dependent because it's periodically time dependent, but now think a bit about, let's say, whether time periodic problems, whether they are actually closer to time independent problems in physics or rather to generally time dependent problems in physics. Just think about this, okay? So, and maybe what I will show you then next time is that actually there are solutions to this problem with this Hamiltonian, right? So we will find solutions. So this is what is called the Floquet eigenvalue equation, okay? And now, I mean, I will tell you next time that Floquet theorem essentially tells you that any solution of the Schrödinger equation generated by this Hamiltonian can be obtained by solutions of this eigenvalue equation. And in the light of this statement of this eigenvalue equation, I ask you whether these, I mean, quantum dynamics generated by such time periodic Hamiltonians, whether they are closer, in some sense, closer to time-independent problems in quantum mechanics or time-dependent problems in quantum mechanics. Is the question clear? And not only to the first two rows, but let's say, I mean, let's say, I mean, please tell me, do you understand which question I'm asking? Right, because in quantum mechanics often, right, you have either Hamiltonians, you can have a Hamiltonian, you have autonomous problems, autonomous. What does autonomous mean? Autonomous is an academic fancy term for saying time independent, okay? So this means H equals H of t, but not depending on t. No explicit time dependence, right? So then if you have this, then your unitary is e to the minus I h t over h bar, right? Okay? Also clear in the more rows in the back? Yes? You follow me? Yeah? So while if h is time dependent, so then how do you have to amend your unitary in general? You have to have this integration, right? And then you have to do time ordering operator and all this nasty stuff, right? So therefore it becomes quickly much more complicated, right? But this then allows for any time dependence of h, right? So then if you do this integral, right? And now you have a special class of Hamiltonians which are periodic in time. Now here in a very simple way, because it's even harmonic in time, right? But let's say it can be just periodic in time. And then we will see that we can give a general solution to this kind of problems by this eigenvalue equation, right? And so now this question, whether this is now closer to really autonomous problems or to truly time-dependent problems, is tantamount of asking, is this reminiscent of the stationary eigenvalue equation or reminiscent of the time-dependent Schrödinger equation? Okay? And so I ask you to contemplate a bit on that, and then the resolution will come next time. Okay, thanks very much.